Okay, welcome to the session on motion planning. A short announcement first. There's an error in the printed program, so for those of you who have planned their talks, so the third talk will be robot task planning and explanation in open and uncertain worlds, which is on the column on the left here, and it will not be robust allocation on RF device capacity and so on. So, just so you know. Okay, so the first talk today will be task and motion policy synthesis as liveness games. It will be presented by Yuan. Please, the floor is yours. Thank you. This is a short talk, 13 minutes and 2 questions.
Thank you. Hi everyone, I'm Yuan. Now we're going to present our project on policy synthesis for robots in an adversarial environment. This is a joint work with Dr. Neil Dutton, Dr. Sua Chowdhury, and Dr. Lydia Kawaraki from Rice University. Traditionally, robots are deployed on assembly lines of factories. Those factories are highly structured environments, and we usually pre-compute a single plan for robot, so a robot can follow this plan repeatedly to accomplish a certain task. In the future, we would like to see more and more personal robots working at home. It would be nice if the robot can help us cook meals and do some domestic houseworks. However, those house environments are usually unstructured, and there are people moving around. What can we do in this case? Can we still use the pre-computation approach? To better understand the challenge, let's look at an example. This picture shows a simple kitchen environment. There's a person moving within the blue region, and the task for a robot is to eventually pick up an object from the storage while avoiding collisions with the person. To be clear, we assume the robot has perfect sensing, and all robot actions are deterministic. We only consider the non-deterministic behavior of the uncontrolled agents, such as the person in this environment. If we still use the pre-computation approach, we may come up with a plan, as the pink line shows here. The problem is that when the robot is executing this plan, if a person moving in this direction, it's very likely that the robot will run into a person, which is not what we want. So as you can see here, the pre-computation is not working. In this case, we need a policy that can guide the robot to accomplish a task. So the planning problem is not to pre-compute a single plan, but a policy that tells the robot what to do based on the current state. So the problem has 3 components in inputs. First is the high-level task specification, and the second is the geometric description of a robot environment. And we also have a set of available actions for a robot in the environment. The goal is to automatically generate a policy that accomplishes this task. So as we can see from a previous example, there are several challenges for dealing with this policy synthesis problem. First, we have uncontrolled agents in the environment. So what's the problem model that can unify reasoning for these uncontrolled agents and planning for robots? In a second, since we need to consider all possible behaviors of all these uncontrolled agents, we may need to deal with a very large state space. So how can we efficiently synthesize a policy in such a big space? Recently, there has been a lot of work on the integration of task and motion planning, and they have shown that the high-level task planning can benefit a lot from information learned from a low-level continuous geometry. Can we extend this idea to speed up our synthesis process? So our work tries to address these 2 challenges. There are 2 contributions of our work. First, we propose a game formulation that models the synthesis problem as a game between a robot and environment. And we propose a synthesis algorithm that can utilize geometric information to speed up the synthesis process. Let's begin our work on similar problems. Most of the task and motion planning problems work on static deterministic domain, where a single pre-computed plan is sufficient. While in our case, we focus on a certain domain where we need a policy. For a certain domain, there are 2 kinds of problems. The first deal with stochastic systems, while reactive synthesis solves a similar problem. The difference is that they synthesize controllers for complex dynamic systems, while in our case, we focus on pure geometric mobile manipulation. Since each arm of the robot has 7 degrees of freedom, this high dimensionality brings new challenge. As I mentioned before, we model this problem again, and in particular, we're interested in Leibniz gain structure. For Leibniz gain structure, it has 3 components. First is the state space of the again. This is a condition product between the robot and the environment states. The second component is the transitions of the again. This defines the valid moves for robot and the environment. Finally, we have a winning condition. For Leibniz gain, the winning condition is defined using a set of goal states. And the winning plane should eventually visit one of these states. So the solution to this game is a policy that selects a proper action for every state for a robot. Now let's see how we reduce this problem again. On the left side is the components of our original synthesis problem. On the right side is the components of our Leibniz gain structure. First, we model a continuous geometric distribution using a data structure called placement graph. This placement graph is our discrete abstraction of the continuous portion of the problem. And those in the placement graph represent valid states, while the edges represent valid motions. And this placement graph also defines the state space of the game. We encode the actions of the robot environment as constraints. These constraints represent the valid system transitions of the game. Finally, the Leibniz task specification corresponds to our Leibniz green condition. Now, the problem of constructing a policy for a problem is reduced to the problem of finding a winning strategy for this particular game. Now, let's look at details of algorithm. We extend the counterexample guided inductive synthesis algorithm to develop our own policy synthesizer. This picture shows the overall structure of the SIGIS framework. In a nutshell, this SIGIS framework is an iterative guess and check loop. So the candidate generator will pick a candidate from a given set of possible implementations of a policy. This implementation may be invalid, so we need to check the policy with a policy verifier. So as we mentioned before, we use first-order logic constraint to characterize the correctness of the policy. So the validity of these constraints can be checked with off-the-shelf SMT solver. If the constraints are valid, we find a winning policy. Otherwise, we will get a counterexample from an SMT solver. This counterexample is open. It's a particular state that the output of the policy is incorrect. So we can use this counterexample to get the next iteration of the search. This algorithm will iteratively generate a candidate and verify its correctness until it finds a winning policy or proof that the policy exists. However, we cannot directly apply this algorithm. The reason is that the state space of the problem is very huge. So we may need to use a huge number of iterations before we converge to a winning policy. So our solution to these issues is to add an additional component called the geometric-based generalization. This generalization component will take a single counterexample and apply heuristics to generate a set of similar examples. And this generalization will help us learn more than one counterexample per iteration and reduce the necessary iteration numbers. That helps us improve efficiency. Now let's look at one example of our generalization heuristics. To go back to our motivating example, this kitchen environment is a special instance of a more general pursuit evasion game, where the robot is the evader and the shape is the pursuer. To ensure safety, we must guarantee that the robot is not captured by the shape. So if we check this invalid policy, we may get a counterexample as a picture shows here. This tells us the location of the robot and the location of the shape. We can explore the geometric relations between these two locations, such as the orientation and distance, and then use this geometric to generate similar counting examples as this picture shows here. So the blue pair is the original returned counting example, while the red pairs are the counting examples we learned using the geometric relation. For experiments, we evaluate our approach using the same kitchen environment. In this environment, there are two persons moving within the blue region, and we test our performance with the increasing size of the blue region. The task requirements is the same requirements. To demonstrate the scalability, we also compare with an alternate synthesis tool called GL1 synthesizer. This GL1 synthesizer is a backend solver of a robotic synthesis tool called LittleMo. LittleMo uses a restricted fragment of linear temporal logic to model the problem. I want to mention here, this is not a fair comparison because we have more knowledge and we apply domain-specific heuristic to speed up the synthesis process. Now let's look at the results. The x-axis is the size of the blue region, and we show the synthesis time with respect to the increasing size of the blue region. One thing to note is the synthesis time is represented in semi-log scale. So for the blue dots is the performance of our approach, while the red clouds is the performance of the GL1 synthesizer. As we can see here, for small size problem, GL1 synthesizer performs better. This is because there's an overhead in our approach. The pre-processing to games and the communication between SMT solvers has some cost. However, for large size problems, our approach has much better scalability in its tested benchmark. To show the gains from a generalization, we also try to remove the generalization component and test our approach without this generalization. So this red triangle here shows the performance of our approach without generalization. As we can see here, without generalization, the approach cannot scale. So generalization gives us orders of magnitude speed up. In summary, we propose a synthesis algorithm for solving process synthesis problem in adversarial environments. We use this game model to formulate this problem. This algorithm can utilize geometric information to speed up the synthesis process. And we show that in the tested benchmark, we have better scalability compared to another robotic synthesis tool. For the future, we would like to incorporate more kinds of uncertain sources. For instance, the sensor noise of the task of the robot. So in this work, we assume the robot is perfect sensing, but in real world, there is always a lot of noise in the sensor. So how can we extend this current system to handle sensor noise is very, very interesting direction. We also want to investigate additional generalization heuristics so that we can solve more problems in a more broader domain. With that, I'm happy to take any questions. Thank you.
Thank you. Any questions? No? I have a question, actually. I have several. So, you mentioned that initially that your challenge derives from the many degrees of freedom, right? Is that what really entails the computational challenge that you have here, and how has that really affected your choice of, or the specific choices you've made in these solvers?
We handle head additionality using the sampling-based motion planning technique. So the placement graph that we use to abstract the continuous domain, this is constructed using the several calls to the sampling-based motion planner. So in this case, we can have a very succinct representation of the continuous space, and this helps us speed up the synthesis process.
I had another question while people think about their own questions. The other question I had is that you mentioned you use a guess and check approach, right? Why? And would there be, is there any other way you can do this? Why specifically that?
So another way to do this is directly synthesize the policy from the extremes. And some of the SMT solver has the capability of directly synthesize the function from a given first order logic formula. We also tried this approach at the beginning, but the problem is that constraint is very complex, and it often takes a very long time for the SMT solver to generate a function, even for a very small problem. So we move to this direction using this guess and check formulation. And this guess and check formulation is very popular in the program synthesis community. So a lot of framework, program synthesis are developed using this framework.
Anyone else have questions? Yes.
So, when you're talking about such highly redundant robots, you said there are a lot of degrees of freedom, right? I mean, I don't know whether you are aware of this, but if you really go back in history, like starting from 1980, there are so many people who have worked on this obstacle avoidance, and from robotic control background, or maybe like in AI, people who are from AI community as well. I mean, so I really don't understand, like, is this problem still open to avoid an obstacle? I mean, there are so many methods available already, like, so do you have to like model this as a game or something? And another problem is like sometimes nowadays, since we talk about collaborative robotics, sometimes human might not be an adversary to you. So then you will have to switch the mode anyways, in your approach, right? I mean, so I don't know whether my question is clear to you. If you want me to explain further, I can.
If you have a brief answer, that would be good.
So the question is about what is the newest approach compared to other previous work, right?
I mean, I'm not yet sure whether this problem of obstacle avoidance in itself is open, right? I mean, because there have been so many works from 1980s onwards, like from different communities, and I don't want to like quote all the work here because of the time, but we can quickly talk offline. So, I mean, since you chose this problem, I was wondering whether this problem in itself is open right now to actually choose it to further develop the solution.
So I think most of the previous work, there are several layers for task planning and the motion planning. So recently, the integration of the task and motion planning has been attracting a lot of interest. So in our case, we are trying to propose an integrated task and motion approach for this adversarial domain. So that's our motivation for modeling this problem in this formulation.
Maybe you could continue this discussion offline. It seems like a bigger issue than
that's very good.
But thank you. Let's thank the speaker again. Okay, so next we have a talk on strict theta star, shorter motion path planning using non-taut paths. Testing. Does it work? Yes, it works. So the talk will be given by Chun-Hao Oh. Hope I pronounced that decently.
Yeah.
Are you looking for your presentation?
Wow.
That's brilliant.
Oh, this is okay. I know the difference. I didn't I'm not sure why my talk is classified as motion basic path planning to find directional paths. But in the near-goal path planning, we want to find paths that look like this. So the consequence of this is that we have shorter paths and we have paths that don't turn as much. So typical applications, if you want to have a character from one position to another position, and you have a grid-based representation of your map, you want a path that looks something like this, rather than looking something like this, because the previous one is just preferable, I guess. So A-star directional grids, if you are not familiar with it already, is to consider your neighbors as your successors, and you do an exploration like this, right? And you end up with a path like this. This is A-star directional grids, and you end up getting directional paths. So Theta is an existing algorithm. It's probably one of the better ones out there right now, because it is pretty simple and it outperforms many of the other algorithms in terms of path length and running time. So a brief description of why it is, because I need this to explain my algorithm. So Theta algorithm is a variant of the A-star algorithm on directional grids. So let's say you're exploring this, you want to look at a successor B. So you would consider, A-star would consider this path for me. But in Theta, you do a look back to the previous, to the parent, and see whether there is line of sight from the parent to the next vertex. So if there is line of sight, because this path is always shorter by the triangle inequality, we will pick this path. If there's no line of sight, we will pick path 1 instead. Clear that? So in the end, we get exploration tree that looks something like this. You compare A-star and Theta, that's how we would explore. So the thing about basic Theta is not optimal. And one of the, and a little more than being not optimal, the paths that we see over here are clearly not optimal, because we can see that we can shortcut there a little and we actually have a shorter path, right? Over here. So if we shortcut this, we could have a shorter path. This is example 2, over here and here. If we shortcut these two, we could have a shorter path. This one as well. If we shortcut this, we could have a shorter path. So one of the reasons why these things are not optimal, I mean, why it's clearly not optimal, is that we can see that these paths are not taut, as in you could pull on the string and make it shorter. Yeah, so what is a non-taut path? Oh, this one.
Get your mobile.
Yeah.
And your heart will continue to beat. I know it's hard to believe without your mobile.
Alright. So, okay. So, non-taut paths. So, one of the reasons why this is not optimal is because the paths are not taut. Clearly not optimal because it's not taut. And non-taut path, what is a non-taut path? Something that if the path, you treat the path as a string, if you pull this, you could get it a little shorter, right? Because this is not really formal definition. So, more proper way to define taut paths is for every heading change, which is a turning point in the path, you have an obstacle that supports the heading change. So you can't pull it shorter because of that. So my algorithm strict Theta start, which is takes advantage of using taut paths to plan shorter paths and also shorter paths, because taut paths are more convincing to a user. So strict Theta start, some of the properties, it is pretty easy to implement an algorithm. I try to keep it as simple as possible. No complicated things. Shorter paths the path turns like this, you just check whether this tau is blocked. If the path turns like this, you check whether this tau is blocked. If the path turns like this, you check whether it's blocked. Because there's no possible obstacle that can support it. Yeah. So the advantage of taut path restriction, so a trace between, this is the original data star, what it will look like. And you can see over here that it will explore this, and at this point, it's not taut anymore, and it will eventually reach this goal. So strict data star, when it comes here, you can see that it doesn't want to explore that. So it's relaxed but with a penalty. So it will pick the shorter path later on. Yeah. So I mean the other two paths, strict data star also fixes the issues for the other two cases as well. Yeah. So not only is there strict data star, we also have a recursive version which performs a little better. So recursive version, here's the basic idea. I will explain it in detail here. You do a recursive loop back until you find a taut path, then you stop. So results. So the reason why this thing is here is the results. So this is on the maps, on the benchmark maps. We have the ones on the right are the benchmark maps. So opticals, BSD maps. You can see that strict data star has the paths. This is data star, this is strict data star, this is recursive strict data star. And these are the path lengths, it's a ratio to the optimal. One is the optimal, so it's at the bottom. And here is the one. Yeah, the original data star is already pretty close to optimal, so it's already pretty good on its own. What you can see over here in the base and game maps, we actually have a pretty significant difference, especially here. Here is strict data star, you can't see it really, because it's strict data star over here. Running time, just to check that it's not really much of a difference. So this is a data star, strict data star, because it's strict data star, about the same. A little slower, I guess. But I did some additional tests between the time I submitted the paper and now. This is on larger maps, up to 5,000 by 5,000. So this is on sparse maps, 6% of tiles. Most paths are pretty close to optimal anyway. And these are the 500 by 500 to 5,000 by 5,000. And denser maps, you can see a more significant improvement over here. Yeah, and running times still about the same. Yeah. Another advantage is we have more taut paths. Now taut path means more convincing paths. This is the original data star. I explain this in a bit. So this is 6.7% optimal. Is the big part over here is the optimal percentage of optimal paths. This is the percentage of taut paths. You should know that all taut paths are actually optimal. No, all optimal paths are taut. Yeah, all optimals are taut. So taut paths are also optimal. Okay, no. I don't know how to say. Optimal paths are taut. Okay. 12% taut, and the rest are either optimal or not taut. Okay. So basically, data star looks something like this, and strict data star looks like this. Higher percentage of taut and optimal paths. As you can see, these are pretty large maps, and the larger the map, the lower the percentage due to law of large numbers and stuff like that. And because it's strict data star, almost all the paths are taut and pretty close to all of them are optimal. Yeah. So that's what I can say about strict data star. It's easy to implement, much of the paths, low runtime overhead. My implementations are over here alongside other any angle path planning algorithms. I'm also working on other algorithms right now, like using visibility graphs to improve grid-based path planning. Yeah. So if you just put any angle path planning like it here, you can get yeah. So interesting framework it would be maybe to try to use the same idea of taut path restrictions for other algorithms. Perhaps you could find more convincing paths just by this simple change. Yeah, that's about it. Yeah. Yeah, I have some additional slides which I prepared just in case you guys have some specific questions. If you guys are the right way
to see those slides. Stefan.
So there is a geometric solution with the visibility graph that you talked about to this problem. The rubber band, you compute the visibility something, and then you search within that graph. So is that how you computed the optimum, or you just that the algorithm one line?
You mean this algorithm is optimal?
No, it's not optimal, I saw it.
Okay.
No, but with the visibility graph, it is optimal. So
yes.
if you run this algorithm, is it how you compute your optimum?
Yes. Alright, okay. The original for this one, the optimal paths were computed using visibility graphs for the benchmark maps. And for the larger maps, the up to 5,000 by 5,000, because visibility graph just put it right on those. I am working on another optimal algorithm that actually allows me to compute this. Yeah. That one I can guarantee is optimal. So yeah. Any other questions?
Okay, let's thank the speaker again. Thank you very much.
Yeah, if anybody is interested in the area of programming, you could possibly, because I want to talk to some people who are interested in the same problem. Yeah.
Okay, thank you very much. So, as previously announced, the printed program is wrong, so we will now hear about robot test planning and explanation in open and uncertain worlds. It's a journal track presentation paper, and Jeremy will be presenting it. Yeah, here it is. It's up.
Okay. So my name is Jeremy White, and I'm presenting on behalf of my many co-authors. I should highlight in particular the contributions of Mark Hanlander and Moritz Goebelbacher, who were co-first authors on this paper. It's not talking about motion planning, it's talking about task planning in open and uncertain worlds. So what I want you to think about is, suppose that you bought your first domestic robot and you've unpacked it, and on the day that you unpack it, you want to give it the first task that you have, which is to get you something for breakfast, and to get you something maybe to read while you're having your breakfast. And the problem is for the robot that it doesn't have a map of the environment because you just switched it on. And thus, it doesn't know how to satisfy the task that you have. It doesn't have the entities in its planning domain in order to be able to formulate a plan to go next to solve this problem. So this paper, the first part of this paper, is about how we solve that problem by bringing together some existing ideas from previous papers. So the key idea number one is, first of all, that we're going to layer our knowledge, and in particular what we're going to do is we're going to layer our knowledge so that we have instance knowledge at the bottom, common sense knowledge next up, and then eventually we're going to introduce diagnostic knowledge at the top. And in order to draw strong inferences about a world about which we initially know nothing, or very little, what we're going to use is we're going to use common sense to make strong inferences about the layer below, about the specific world. So, for example, if you switch on your robot, this is the kind of thing that you might see. So you have a little coloured disc there, there's a visual recognizer in the robot that tells it, well, a categorizer actually, which tells it what kind of category of room it is likely to be in. And that distribution there means, purple means that it's probably an office, but it could be a corridor, or it could be a meeting room, or some other kind of room. And that distribution is about the only thing that the robot knows of any significance. But there are there's a little topological map here, and there's a few places in the world. So there's the place that it's at, and there's places, those grey markers, which places that it could go to. And that's everything it knows about this specific world right now. So there's not many inferences that it can draw. If we add, however, some default knowledge or common sense knowledge in the layer above, what happens is we can now make stronger inferences about what's in this world below. So, for example, we can draw the conclusion that the particular place it's at is in a room. We can draw conclusions about the category of the room based on a multitude of different evidence. we can draw conclusions about what rooms it might be connected to and what might be in those rooms based on knowledge about relationships between categories of objects and rooms. So this is fundamental to being able to do this kind of work. So that's the common sense. The second idea that we have is that in order to be able to solve these kinds of open world planning tasks, the robot needs to represent not only what's in the world, but also its epistemic state. So in other words, it needs to represent explicitly in the instance state what it knows about this instance world and what it doesn't know. And furthermore, it also has to represent belief dynamics. It has to represent belief dynamics in two ways. One with epistemic operators, and two with obviously probabilities that we're going to use with Bayesian updates. And that belief dynamics is going to be critical to allow the robot to reason about the knowledge effects of its actions. So, the three kinds of information or predicates that we have in the lowest level state are, for example, just a statement such as office, room 1 is an office, but we can also write epistemic statements such as Dora, the robot, knows that room 1 is an office. And here we have another kind of operator which was introduced in the previous paper, which we're going to make a lot of use of in this paper, which is this notion of an assumptive predicate, which is another kind of knowledge predicate. And essentially all it's saying is that the robot is going to assume, for the purposes of planning, for the purposes of argumentation, as it were, that room 1 is an office, even though it doesn't have completely convincing evidence that this is the case. And using these three, we're going to be able to then write down our belief dynamics. Now, in the paper, we explain a lot of different operating models and characteristics that we have. But the one I'm going to emphasize here is one called an assumptive action. So an assumptive action is very, very simply put this. It is a mental action that has a cost to it. And that cost, broadly speaking, is going to be inversely proportional. It's going to be the inverse of the likelihood of the assumption that you're making. So the less likely the assumption is to hold, the more costly the action is going to be. And then what happens is the effect is to believe that essentially possible fact about the world. And if we have probabilities in our belief state, we can also attach probabilities to those assumptions, as well as having costs. So, for example, we're going to have two kinds of assumptions. The previous one that we used, but we're going to use it again here, is what we call closed world assumptions, or assumptions about instance state from instance knowledge. So, for example, if we have a posterior distribution in our belief state over the categories that this particular room might be, what we can do is we can make an assumption that one of those categories is in fact correct. And we make it with exactly the probability that it holds in the belief state. So, for example, if you believe that the room is an office with probability 0.52, you can then make the assumption that it is the office with certainty. Obviously, that assumption then holds with probability 0.52. And what we do is we create these. The planning domain is obviously created on the fly every time the belief state of the robot is updated. And so we create all these assumptive actions for these closed world, essentially closed world assumptions where you're choosing between one of a number of innumerable worlds. So that's what the robot will be essentially be thinking in that case. However, and the first key contribution of this paper is that we can take the idea of assumptions or assumptive actions and we can combine it with this notion that we've got of common sense. And this is going to allow us to solve the open world planning problem, which we can't solve with what I've shown you so far. How do we do that? We introduce a new kind of assumption. If you think about in your default knowledge, in our default knowledge graph, there are relationships that are deterministic and also relationships that are probabilistic. So, for example, we can say that, usually, not always, if you go to a kitchen, you might find things like cereal boxes or boxes of cornflakes. For this one, we have a cool example, which is that if you go to a meeting room, you'll often find a copy of AI magazine, apparently. So the point is that you have relationships which are statistical between particular objects and particular kinds of rooms. So what the robot's going to be able to do then is it's going to have assumptions that it creates which are based on this default knowledge. But the assumptions that it's going to make are going to be about the instance world. Right? They're going to be about a specific world, but they're going to be based on a combination of the instance knowledge that it already has, plus the default knowledge. So, for example, you're plonked in a room. You don't see the kind of room that you want to have in order to be able to perform the task you have. So, for example, you have a cornflakes box that you want to find. You then posit the existence of a kitchen. So you assume that there may be a kitchen on the basis of some room connectivity rules. And then having done that, you can then make an assumption that there might be a cornflakes box in that kitchen. And if that assumption will hold with precisely the probability that it holds in your default knowledge. And those are probabilities you can actually write in a plan tab, so the planner fills them in according to the default probabilities. This is the robot running. So this is the robot going and searching for a magazine. It starts in an office, it's switched on, it has very little map to begin with, so it doesn't have the entities in its instance map that it would need to formulate a plan. And what happens is it's a continual plan. So it replans every time that it adds new things to the world and that those new things break the existing plan. The colours here, you can see yellow means it's realised that it's a corridor, and it's constantly planning, constantly in a sense reimagining, hypothesising the existence of a meeting room and the object that it's looking for, which in this case is the magazine. When it gets there, it's a switching planner, which was introduced in the previous paper, and what this does is it chooses when to schedule a POM-DP planner, and then the POM-DP planner sequences a sequence of view cones generated with an art gallery algorithm. So it does a fairly efficient visual search of the room, and eventually we'll see the object, which you can see down here as a copy of AI magazine. However, that solves this open world planning problem. But we can go further. What we can do is we can cheat. We can hide the magazine from the robots. And so what we do is we take it and we, rather than keeping it on the table, we hide it in the cupboard down here so that when the robot searches for it, it can't find it. Now the next task that we're going to set for ourselves is for the robot to be able to deal with this failure that we're going to induce in a graceful way. So the first thing that it does is it uses its POM-DP to reason about the fact, or rather in this case, a belief distribution of where the object might be. So it can reason about vision failures, so it will sometimes go back and search in multiple places. But here what it's doing is it can't find it in the meeting room, so it thinks, well, maybe there's a probability that you've left it in the office. So it goes back to the office, searches there, but gives up fairly quickly. And giving up in our scenario here is, I've just realised.
Plan execution failed unexpectedly. I'm searching for an explanation now.
So it fails when the probability of the best plan it can find succeeding falls below some particular threshold, or the cost rises below some threshold. What's happened there is that the robots have a surprise. So in order to explain the surprise, we're going to have to define what we mean by surprises. So what we had in our plan was we had a sequence of assumptions and then some moving and sensing actions. And in this case, what happened was that the robot expected, after it had sensed in a particular room, that it would know where the magazine was. But in fact, the world turned out to be different because it didn't know where the magazine was. So what we need to do is to explain that failure. So an explanation of a surprise in our framework is simply going to be a new plan which involves all the physical and sensing actions that you took, but takes away the old assumptions and comes up with a new set of assumptions that explain the problem. So if you think a little bit like this, you take away your old assumptions, you're going to replan, and you're going to replan a new set of assumptions, and the idea is that new set of assumptions are going to make what you actually expected to see equivalent to what you did see. In other words, that they're going to make it so that the robot doesn't expect that the actions that it would have performed would have led to finding the magazine. To do that, you then have to have additional knowledge, because you have to have diagnostic knowledge in addition to your common sense knowledge. So here you now have knowledge about how actions can fail in another layer, and that enables you to have this explanation of surprises. So rather than just having the instance knowledge at the bottom, and also then having the default knowledge and action models, which are sort of common sense knowledge above, we now have this third layer of knowledge, which we refer to as diagnostic knowledge. And this diagnostic knowledge in our system includes two very special kinds of actions. It includes, for every action in the main domain, it includes an action that allows it to, has additional conditional effects, essentially, that allow it to say all the ways that that first action might have failed. Right? So there's a more complicated copy of the original action model. The second kind is an action that can hypothesize new common sense knowledge. In other words, it hypothesizes new default knowledge. And that's often what we need in the explanation. So here's the robot trying to come up with an explanation. It takes about this long.
I have now found a possible explanation for the failure. Perhaps the magazine is in a container which is most likely a meeting room.
So it comes up with an explanation that maybe we've hidden the object somewhere, and that the place that we've hidden it is in fact inside the meeting room. But it comes up with other explanations as well. So it says, for example, one of the explanations it comes up with is that the object is in fact not in the domain, so it doesn't exist. Another example that it comes up with is that we've hidden it inside the table, because it doesn't understand that tables can't contain things. It then goes and makes assumptions about the fact that it can find a person, and then it's going to go and test the hypotheses. And the hypothesis here is made of 4 assumptions, 2 of which are about new default knowledge, and 2 of which are about this specific world. don't use speech, we just use, we type the natural language, but we're going to speak it for your purposes. Well,
Is there a container in this room?
Yes.
So this is a question about the instance world.
Well, magazines typically in containers.
That's a hypothesis about new default knowledge. So it's a fairly strange robot in some
Well,
sense.
containers typically in meeting rooms.
Yes.
Okay.
And the final question
Is
is
there a magazine in the container?
another instance question. So there's two hypotheses that it's formed that are about instance knowledge and two that are formed about general knowledge. So what's happened here, in summary, is we've taken this notion of assumptions that we previously developed, applied it together with common sense, we've created this new notion of assumptions of default knowledge, essentially, help us to do open world planning, and then by combining it also with diagnostic knowledge, we can do explanation of failure. Thank you very much.
Any questions? Yes.
Can you tell us a bit about how much effort do you have to put to do the modeling and knowledge engineering so that it works robustly?
Okay, word lot. So there's several stages to it. First of all, you have to define your common sense knowledge. So we did that in two stages. Stage number one, we took the open-lined database where people get to type words that they associate with other words. So you write kitchen, and then the people are given free text, and they can write all the objects that they associate with kitchens. Then we need for some of our relations in our default knowledge graph are probabilistic and some are deterministic. And this is work by Andre Granolis, who I think you know, obviously. And what Andre did is he then defined something called the chain graph that allows us to do efficient belief propagation in order to draw inferences. But to get the probabilistic element there, we got some probability by mining web, by doing searches for combinations of the words from the open-lined database. You then also have to build models of your observation failures. So you have to, and those you have to do physically with the robot in the real rooms that you're doing it, because those will be remembered the specific operators that you've got. And then finally, you also have to have the probabilities of particular kinds of action failures. So what happens is that a lot of the assumptive actions, one of the neat things about this is that they are drawn automatically from the belief state as it's updated. So those are actually generated on the fly by the robot. So as it updates its knowledge of the world, it will update it completely. But there's a lot of work in trying to put this together. There's something like 100 different programs. That's why there's 15 authors, because every single one of those 15 authors made a substantial contribution. There's some really not. This is about 10% of what's in that system.
I have a brief question. So the issue of forgetting in AI systems and robot systems has been, in my opinion, a little bit under-addressed. But it is nevertheless very important, because if you want a robot to live in the real world for a long time at least, it's going to start learning more and more things and even instance facts. Can you say that you've made this issue, or that you've solved this issue like this? By representing and proving the falsehood of assumptions on the fly as you do here.
I've never thought about it like that. It's a really interesting way to think about it. The other startups I don't know. We have to sit and have a coffee and talk about it. It certainly wasn't what we planned to do. I mean, I think what I would... Here's one thing that I think is important. It's maybe not to do with forgetting so much as to do with attention, which is that you need to remember not to think about lots and lots of things when you're formulating your plan. And that's the thing that we don't do here, right? Which is that one of the huge problems that's left is saying, hang on a minute, if I've got all this common sense knowledge, one of the classic things that we went to AI conferences in the 1980s, people talked about the knowledge management problem, right? And this is, in a way, is another example of the forgetting thing, which is only remembering the things you need to know in order to be able to reason about your tasks efficiently. And here, you can see, I mean, if you push this to a slightly larger world, because of the state of planners and various other kinds of things, this is all fall over. So I think that knowing what you need to reason about is as important as knowing what you do and you don't know explicitly. But then I think you have to do it tacitly. So I don't think it's quite an answer to your question, but I think it's tangentially related.
Yeah. Thank you very much.
Very tight. No.
Well, really, if it's really quick.
So you're going to have to speak up a bit.
Since defining the knowledge needed in order to control this robot, they implement the effective way for modeling the problem that you, the situation that you are going to address. If you use some knowledge engineering tools or validation, verification, some procedures to test before actually deploying your system, in particular the knowledge part. So to be sure that your knowledge, your models are actually well suited for the specific situation that you address.
Can I speak come up in the meantime?
I think I'm going to be honest and brief about that, because I think, I think to be honest to that, in the sense that what I described about the open world stuff, I thought was a reasonably principled way of doing it, which is that we have, we take it from open minds, we take it from your data, and we take probabilities. But the rest of it basically has to be engineered by hand. And the reason for that is because it's damn hard to get these systems to work at all. So I think that there's a lot to do in that area with that regard. I wouldn't want to claim that we really addressed that problem. Perhaps we've done many principal things, but I think there that was not what we're trying to do. It's a very important problem to solve. Thank you.
Thank you. Running a bit late, but not too much, and it's interesting discussions anyway, so are you going to use your own laptop? Can you have HDMI, please? Good. Okay, so the last talk of this session, this is a long talk. In the robotics track, we will be hearing about robot motion planning for pouring liquids by Pan, Park, and Manansha. And you are the first author, great. So Joe Pan is presenting, thank you.
So, good morning. I'm going to present our work on motion planning system for power liquids. I'm Joe from the University of North Carolina and Gamma Group. So first we cover a little bit background and motivation. We want to solve a motion planning problem for fluid manipulation. Typical applications of this kind is, for example, we want to handle dangerous liquids in a lab, we want to replace the lubricant for a car, we want to clean out the shell of a product. Fluid dynamics play a very important role in all these applications, but here we focus on a special application where the objective is to transfer the liquid from a soft to target container. And we take a motion planning point of view to solve this problem. So in this case, compared with conventional motion planning pipeline, where the goal is to move a robot from a source to target configuration under, for example, collision or additional curvature and cost-saving constraints, we need to deal with new kind of objective as well as new kind of constraints. So in our case, the objective is to move as much liquid into target container as possible, and our constraint is that this liquid discretized liquid elements should follow physical laws, so they're governed by the Navier-Stokes equation. So the challenge in solving this kind of motion planning problems comes in both fluid dynamics and motion planning problem itself. So on the liquid dynamics side, it's already very difficult to represent this highly deformable liquid body. For example, you want to capture the free surface shape. You can either introduce a large set of particles or you can use a general volumetric mesh, but either way, you need to introduce a large number of variables. So this gives you a motion planning problem in a really high dimensional configuration space. And based on this data structure, you also want to predict the future configuration of your liquid body, and you can get some answer to this problem by looking at research in computational fluid dynamics. But today, this kind of simulations are still very costly. For example, in our experiments where we want to predict a cup of water and its configuration over 5 physical seconds, that simulation you want to face with more challenges. So this kind of problem can be generally formulated into the framework of PDE constraint optimization, but reliable algorithm of this kind can only be found for very simplified dynamics and theoretical objective function, which is clearly not the case. In our case, actually, these free surface changes are non-smooth. So you want to constantly update your data structure, either your particle or your mesh, and these procedures are sequential and non-smooth, so that you cannot find reliable gradient information to do the continuous local search to find a feasible solution. So an alternative to work around this problem is that you rely on stochastic search. In terms of robotics, we can call this a sampling-based motion planning, but there's a little bit difference. So if we think of this problem in a sampling-based framework, you need to do a lot of probing using tentative solution, tentative plan, and each such probing involves a separate fluid simulation that takes hours. So finally, the simulation can take weeks, can take months. This is almost infeasible. So before we go into our framework, we first look at how previous works. So this kind of problem. Formally, this is not a new problem. So people have actually tried to solve it by either gradient-based search or gradient-free search. So for example, on the left, we use evolutionary optimization to try to avoid spilling for a spoon of liquid. And since we cannot find reliable gradient information, that takes the optimization takes 100 hours on a cluster. And on the right, we try to control the computer-generated animation of smoke. And smoke is much simpler than liquid because we don't have a free surface. And we don't have non-smoothness, so that we can find reliable gradient information. This helps us to greatly reduce the number of probings we want to use to find a feasible solution. And that takes about approximately a day on my desktop PC, but this is still a long time. So people have also think about how do we first reduce the overhead by using not the aggregate model, but an approximate model. So in this work, we replace the liquid body by just a set of rigid particles, and we ignore the interacting forces between these particles totally. So such simplified model can help us to do high-level semantic planning. We can generate a pouring-like motion, but this is not accurate enough to do explicit control that guide liquid into a target container. And finally, a parallel research that has proven to be very successful, this is also published in our university, is through imitation learning, where you collect a lot of successful pouring trajectory from human, and you learn policy by supervised learning. And this policy can help you to mimic the motion of pouring on a similar setting. But if you want to extend this method to more general settings, in our case, maybe new container positions, this is really risky because this method ignores dynamics. So based on these previous works, we propose a new motion planning pipeline. So the key contribution of our work is that we combine an accurate fluid model and a simplified fluid model. This simplified fluid model helps us to define a reliable gradient information so that we can use efficient optimization-based motion planner to find a tentative solution. And the accurate fluid model is used to compensate the error introduced by such simplification. Since currently we haven't experimented our system on a real robot, we need to build a fluid simulator. We use a classical algorithm called FLIP, which is based on hybrid particle mesh representation, and we also incorporate a laminar viscosity term so that we can experiment with different fluid materials, ranging from water to more viscous materials such as jelly, honey, or milk. And we also want to verify how accurate the model is. So we simulated the pouring of different fluid material on the different resolution. In our case, different particle radius. And as we can see in this chart, as we double the resolution, the error with respect to the ground truth is approximately halved at each time step. This proves that our solver is first order accurate but still convergent. I want to emphasize that convergent means as you increase your result doesn't change, but that doesn't mean this solution is consistent with real-life experiment. Currently, no fluid simulator can give you such a theoretical guarantee that the result is consistent with a real-life experiment. So based on the observation into data generated by this accurate solver, we build our simplified model based on analysis into the particle streamline. So the guideline for this simplified model is that it should be very easy to evaluate, and it's a continuous procedure so that we can compute gradient. And the model is restricted to the application of liquid pouring. It's not a general model like our accurate method. So if you take a look at the streamline of each particle in the course of pouring, you can see that we can decompose this into 3 stages. In the first stage, the particle stays in the source container, and its motion is largely influenced by this plan, by your source container trajectory. And then it follows a free-flying curve, which is a green curve here, before it falls in the target container, which is a blue curve. So this is the green curve, the free-flying curve that we model. In this stage, we assume that gravity force is the major force influencing the particle motion, so that we can introduce the assumption that this curve is a projected curve. We can verify our assumption by fitting a projected curve to the streamline of each particle in a least square sense and profile how many particles can take such approximation, but with only marginal error. And in this chart, we can see that independent of what resolution we use, approximately half of the particles can take such approximation. We discard other particles to avoid misleading the optimizer. And our second assumption is much stronger than the first one. We assume that if you slightly perturb your source container trajectory, basically your plan, the intrinsic shape of the streamline doesn't change. So this basically means that each particle streamline is rigidly attached to the source container. This is a very strong assumption. It almost totally ignores the fluid dynamics. So our method is to correct this assumption by using an accurate fluid simulation to find a new, to update the streamline. So here's our planning pipeline. This is a 2-stage method. In the first stage, we use a general optimization-based motion planning framework that can take various constraints. And we also add our liquid pouring constraints based on this simplification. And the second stage is just a accurate fluid simulation to correct and to fit the new projected curves. So one advantage of our method is that it's very easy to be integrated into an existing optimization-based motion planner. Our current method of framework is based on the pipeline of chunks. So if this is the outline of this chunk framework, and to modify it to account for liquid pouring, we just add these blue blocks. So before each iteration, we perform an accurate fluid simulation, and we fit the projected curve to each particle streamline, we generate valid particles. And then we do a numerical optimization, but we add this pouring objective. So currently, we consider several kinds of common constraints, such as collision avoidance against the static and dynamic obstacles. We penalize the behavior of moving too fast when you're close to an obstacle, and we also penalize any penetration depths. We also add simple regularization favoring smooth trajectories. And based on this projected curve assumption, it's very easy to add the pouring objective. We just penalize the distance between this projected curve and the target container center opening. So this is the distance between the projected curve and the point. This can be computed analytically, and the gradient information is found numerically by numerical differentiation. But if you just use this simple formulation, it's very likely that you can get a triple solution where you just don't move your cup a little bit and no particle streamline can generate it. So we use a very simple initialization by replacing this objective with initialization term that try to lead the cup, the source container, to a target leading angle so that liquid can pour out and we get the initial set of trajectories. finally, we present some results generated by this method. In our current setting, we use 50,000 to 60,000 liquid particles, so that if you just formulate this as a general PD constraint optimization, your total degree of freedom can be several million, because you need to determine the particle location at each time step. But our method only requires pure simulation, not optimization. Still, this simulation takes hours, as I have mentioned, and this is really the bottleneck of the framework. Compared with this stage, the optimization itself, both the initialization and the iterative update, takes less than 10 seconds. So this is a marginal cost. But the benefit is that our method can converge after only a few iterations. For example, we experimented with a different fluid material and different source container shapes. In this case, with small viscosity, for example, you are experimenting with water. After 2 fluid simulations, you get convergent result. Almost all liquid particles falls in the target container, as in the second row. And we also experimented with a wide open coffee map. But this is more challenging because your outflowing rate is much larger. Still, after 2 iterations, we get convergent result, but there's some overshooting in the initial stage, which cannot be removed by further iterations. When you experiment with more viscous liquids, this is more challenging because the fluid dynamics play a more important role in this case, and we ignore all these dynamics by our simplified model. So it takes more iterations to converge, basically 4 to 6 iterations. And one interesting thing in this optimized trajectory in the second row is that we regenerate the back force adjustment, which is very similar to the shaking motion human will do to force a jelly liquid out of a container. And finally, here is the live demo showing method working with a general obstacles. And this is with a smaller viscosity, so that you get a little bit turbulent flow, but still projective approximation gives you a really good prediction of the mean flow direction. You can see that the flow is more turbulent, but still we can get the mean to the target container. And in the second set of experiments, we use a more difficult, more challenging obstacle shapes. And we also experiment with a target container with volume much smaller than our source container. But at the current stage, we don't model speeding. So that we just cut the simulation after we detect that the target container has been filled up like this. Again, with a smaller viscosity. I just conclude. So what we have proposed is a motion planning pipeline for solving liquid pouring tasks. So the contribution is that we combine simplified model and an accurate model. And the simplified model provides gradient information to local search, and the accurate model compensates the error. But there are still some limitations to our current work. So clearly you have seen we do model speeding. And a big issue of this pipeline is that can we get conversion or we get monotonic behavior of any kind. So in our later version, updated version this year, we incorporated a very simple line search strategy to ensure that the solution converges by blending the solution of consecutive iterations and tune this blending factor in a similar way as a line search, so we can smooth dynamics, this is still a challenging problem. So I think our framework can still work. And the projected curve assumption is still correct. So I believe if you replace your simulator with a DEM simulator, you can get similar results.
Are you planning to extend your work also considering the dynamic position of objects or obstacles? And for instance, envisaging in the human presence also the possibility of humans moving around, so having some probabilistic approach to envisage what the humans is going around.
I think it's very difficult to incorporate the dynamic obstacles. It's not a problem with optimizer or use existing channel that can take that dynamic obstacles. The problem is that our simplified model doesn't model speed. So if you use you plan equals to biological motion of the source container, then most of the liquid will miss a lot of liquid from speeding, and we don't model that. I think this is a very interesting future work.
One more question. So, just one question. So, when you have the CFD models, have you considered other effects that could actually influence this action of pouring liquid into a SI? For instance, I don't know whether you would have noticed if you would have taken one of those ceramic coffee mugs and you try to pour. If you pour it with a very small, velocity, it would not fall to the glass. It will just fall down like this. Instead, if you take a glass which has got sharp edges and if you try to pour, what I'm trying to say is the kind of the brim that you have on the glass, it also influences the motion. And this is just one example. There could be so many other factors like if there's wind or like. So when you just go by this model-based methods like this CFD, and if you don't rely on some perception modules to actually check whether it is really going inside or not. I mean, have you considered those effects as well?
I think this is a good question. So, a very important feature what we're considering is to use system identification in place of the CFD model for two reasons. So first is that it's not consistent with the real-life experiment. And the second is that we want to consider more difficult scenarios like the moving target container. I think you're talking about that, right? You're talking about the case with moving target container.
Are you saying in brim, for example, if you have a beaker, if you pour something really slowly, it starts trickling on the side of the cup.
Yes.
I mean, this is just one example. There could be so many other things in the environment which actually influence your fluid motion, not just the viscosity, for instance.
I think our current simplified model doesn't count for surface tension effect you have talked about, like dripping. So this is also another reason why we want to consider more general system identification in the future.
Okay. Thanks, the speaker. Again, I was
machine learning techniques which do that. So one of my lab mates, he works on that where allows humans to teach. Okay, so if even the target container is moving at certain velocity, and human will have like 4 or 5 trials and human will adjust itself. First time he will go, first time he will whatever. So based upon how human is you learn certain parameters, what is the rate of your tilting, what is the type of bottle you have, and what is the rate the other container is moving. You learn certain parameters and then simplify a model and then make the robot do that. Because this framework, I don't know why they have used it, it's kind of outdated, especially when it comes to liquid pouring, because it's not generalizing. In real world scenario, the target container can never be stationary. It's like impossible. In real world, even if you are pouring some dangerous liquid,
not just the container being stationary, even the kind of print that you will
So
there are many things that could actually influence this motion.
So now what will happen is you
can create a model of humans learning, right? So same thing, if it's a bottle, it will be different. If it is a beaker, it will be different. It will be a plastic bottle, it will be different. So in that way, now as humans are training it, after 5-6 trials, the robot can learn easily.